I'd like to introduce Bertrand Toën from Montpellier, who is not very favorable role of giving the first talk after the conference banquet. He's going to speak on symplectic and Poisson structures in the derived setting.
Thank you. Thank you very much for the invitation. Thank you very much for the dinner. The beer before the dinner and the beer after the dinner was very nice. Okay. So this is a joint project with various people. Tony Pantef, Michel Vaquier, and Gabriele Vezzosi. And also some part are in collaboration with Daniel Kalak and Katsarkov. So it's a project. It's an ongoing project, and we think we have made some progress recently. So this is what I will try to explain today. So let me start by stating a theorem. And let me put a little star here. If you remember before the end of the talk, ask me what the star means. So K is a field of characteristic 0. X is what can be many things, but it can be either a smooth projective Calabi-Yau variety over K. So here it comes equipped with a trivialization of the canonical sheaf. Or it can be an oriented, compact, topological manifold. Or it can be any reasonable oriented object. Well, let's keep in mind these two first cases, but I just wanted to say that it also applies to some other cases where it's close enough to be either a Calabi-Yau variety or an oriented compact manifold for the theorem to be true. G is a reductive group over K, and I want it equipped with a G invariant scalar product let me try to do this. Then the theorem states that the derived moduli stack burn G of X of G bundles on X admits a canonical let me put it that way, n quantization. And n here is 2 minus d. D is the dimension of X. So 2 minus d of X. Okay, that's the statement. And the purpose of the talk is to try to explain what it means and to explain a part of the proof. Okay, so the purpose of the talk to explain part of this statement. So let me start by telling you a little bit more about what this quantization means here. Maybe I should first say something about this word, derived moduli stack. Well, I just want to say that I'm not going to insist on this aspect. You can just think that this is a moduli space in the sense it's an algebraic variety whose points parameterize G bundles on X. And you have to look at this algebraic variety in a rather fancy way. But it's close to be a variety. So I will act as if it were an algebraic variety. Just either you know what a derived stack means, and then you're fine. But if you don't, just think it's an algebraic variety. And maybe there's a bit of extra structure on it that makes it better behaved than just a moduli space as an algebraic variety. So let me just not insist on this part because it would take too long. And I want to give a little bit more, to say a little bit more about this n quantization. So let me denote by Z this moduli space. I can look at sheaves on Z. Z is an algebraic variety or a derived stack. I can look at sheaves. And I can take the derived category of sheaves on Z. That's the derived category of quasi-coherent sheaves on Z. So if Z is an affine variety, this is just the category of the derived category of the ring, the corresponding ring, say.
What would it be in the topological case?
Sorry?
What would it be in the topological case?
Which topological case?
The oriented compact manner.
When X, you mean? This is still an algebraic variety. And say, I will give examples, low dimensional examples, but if X is a surface, dimension 2, then this is essentially the character variety of the fundamental group, and this is just the derived category of modules over the ring corresponding to this affine algebraic variety. More or less. There is this tacky thing, but it's more or less this. Let me put a little DG here. I think we've heard about DG categories in some previous talks. So it's not really a category, but it's something with more structure. Right? Like I want to look at it as a DG category. And these kind of quantizations, by definition, are formal deformations of these DG categories. So an n quantization of Z, by definition, means a formal deformation of this category. But there is an n here. I have to say in which sense I deform the category as any n monoidal DG category. So sheaves form a symmetric monoidal category. I can tensor quasi-coherent sheaves. And so it's an E infinity monoidal category. So I can look at it as an En monoidal category for any n. And I can look at deformations of this En category, formal deformations of the derived category as an En monoidal DG category. That's what n quantization means. And you'll see that n can be negative here. So I should really say, I just take the absolute value. And there is a trick now, is that the formal parameter is shifted. Q as a degree now is of degree 2n. Okay, that's again, that's kind of a small trick. So it makes sense to talk about not, it doesn't make sense to talk E minus 1 or E minus 10 tensor DG category, but it makes sense to talk about deformations of these things. Deformation of an E infinity, of an En DG category, say, when n is negative. Makes sense by just shifting the formal parameter. Okay. Okay, that's what I mean by quantization. So this is a quantization which is deformation quantization. It's not geometric quantization. And let me give questions maybe.
No, I just pointing out that the dimensionality of Planck's constant is action.
Sorry?
The dimensionality of Planck's constant is action. So there's no contradiction with physics here.
Great.
Yeah.
I'm glad. Well, for n equals minus 1, you can find this kind of thing in some paper of Kapustin. There is this trick, but so low dimensional examples. Quickly. So in dimension 1, 2, well, 0, 1, 2, 3, this quantization in this sense can be actually seen. Let me start with dim x in 0. Just like this a point. Then G bundle on the point is not really a point. It's a point, but the trivial G bundle has a lot of automorphisms. So it's a stack which is called BG. You can look at it as a groupoid with one object if you want. So it's a groupoid with one object and G as automorphism. So this is my Z. Now D of Z is just the derived category of representations of G, algebraic representations of G. Because quasi-coherent shapes on BG are just representations of G. And here n equals 2. So I should give you a formal deformation of the category of representations as an E2 monoidal category, which means as a braided monoidal category. And this is the quantum group. With respect to, well, I have fixed this scalar product, so I use this one to define the quantum group. So, which is a deformation of D of Z as a E2 monoidal category. Let me skip dimension 1. There is something to say in dimension 1, but I don't know the terminology. So let me skip it. It's not really relevant. So in dimension 2, let's assume that X is a compact oriented topological surface. Then G of X is essentially the moduli space of representations of pi 1 of the surface with coefficient in G. So that's the moduli of representation pi 1 in G. And let me give a part of this quantization. Here, there is you can restrict to the smooth part of this. You can make it into an affine algebraic variety. Restrict to the smooth part, say. That's the smooth part. And it's known that this is a symplectic variety. So I can apply deformation quantization to this symplectic variety. And essentially, if I work with affine algebraic variety, this is the why functions here are the same thing as functions on the ring, which classifies the universal representation. So it's functions on the character variety. And this deformation here is like called the skin algebra, something well known in low-dimensional topology. So this is a case where also this quantization has been identified. And so n is 0 here. I'm just deforming essentially O of u deforms as a non-commutative algebra. This is what this deformation quantization does. And I can recover just if I apply derived, say, let's give a name, O of u little q. So I get a deformation on the category of modules and on the derived category. So this is the deformation. It's a deformation of categories now. So it's E0 monoidal. E0 monoidal means no monoidal structure. It appears in how I define G bundles on something topological. It is defined in a way that these are local systems of G torsors or something like this. That's by definition. It's not, X is not a smooth anything, it's just a topological space. And by definition, G bundles on the space are locally constant objects, just by definition. Okay. And the last example is in dimension 3, which is not very clear, but I want to mention one thing. So let's assume that X, let me give, put myself in the algebraic context. So X is a Calabi-Yau threefold. I will write a mysterious sentence like this. So it's a -1 quantization of this moduli space of G bundles on X is closely related to Donaldson-Thomas theory. There is something precise to say, but it will take a little bit. Let's say that. So this -1 quantization is a deformation as a monoidal category. And you can, well, essentially you can interpret the Donaldson-Thomas invariance using this deformation. Let's put it that way. So it's also something, maybe this deformation as a monoidal category is something a little bit new, but it's very much related to something classical. But it becomes completely new in dimension 4 and higher. I think this is completely unexplored. So when the dimension of X is bigger than 3, this is unexplored. By this I mean we are able to produce these quantizations and we don't know to what they are related. I don't think this has been studied actually, but you know, you can take a smooth part of the moduli space of bundles on the K3, and there is a symplectic form there, so you can just do deformation quantization. I don't know if anyone has studied this or not. You know?
That's right, but that's not obvious that that's the same as a deformation of the global derived category. If you actually wanted to deform the derived category just as a category.
No, it's the same. I mean, by definition, it's the same. Okay, look, I'm never going to talk about anything else than deformation of categories. Okay. Anyway, in many examples, you can write this deformation as deformation of rings, but sometimes it's not possible. And well, anyway, I don't know. For the case of K3 surfaces, I don't think. I mean, I've never seen any reference where this has been distributed. But it's take a part of the moduli stack which is smooth. There is a symplectic form, so you can do deformation quantization. I don't know if anyone has done this.
Did you? I'm sorry, I didn't notice. Did you assume G was simply connected?
Sorry?
Did you assume G was simply connected?
No.
Because if it isn't, aren't there some torsion subtleties which might lead to different choices among your sort of not formal?
Simply connected, no. Connected probably, but simply connected, no.
But I mean, there are different. Somehow there are. Oh well. Okay, maybe.
I don't assume it's simple.
Yeah.
I want to apply this to GM, for instance. Really an interesting example. Okay, so what's the main step of the proof of the theorem? And then I will isolate a part of it, which I want to discuss in more details. Steps. So step one is to construct symplectic structures. So it's a result saying that G on X carries a canonical symplectic structure, but it's not a symplectic structure in the usual sense. It has a shift. So I will say of degree n. So I'm z-graded here. It's a little bit like in supergeometry where you have even and odd symplectic form. But here I have forms of any degree. I'm not working with z-mode to the graded object. So what does this mean? Well, first, this is a theorem, which is well understood. It's written down. You can check on the web. There are also many extensions of this result to various settings. For instance, X can be a manifold with boundary. So Damien Calac has proved the version with boundary of this kind of thing. There is a non-commutative version where you can take X to be a non-commutative variety in some sense, and so on. So there are various extensions, and this is completely well understood. Let me just say, what kind of structure is this? So it's a non-degenerate pairing on the tangent sheaf of this object here, and this is where these derived algebraic stacks are important, because this, if you just look at it as an algebraic variety or as an algebraic stack, the tangent of this space is pretty bad. And derived algebraic geometry is precisely here to make infinitesimal computations easier. So what I will write here only makes sense in derived algebraic geometry and is completely false in algebraic geometry. Even if you use algebraic stack, you really need to use derived algebraic stacks. So it's a non-degenerate pairing on the tangent sheaf, which is here a tangent complex, really. I will still denote it by Z with a shift. So where TZ is the tangent complex. Of Z, which is the G of X. And this pairing is very natural if you look at it pointwise, it's quite natural. Assume that I have a point in the moduli space of G bundle. It corresponds to a G bundle on X. I can describe this, the stock of this sheaf at the point ρ is a complex which is the cohomology of X with coefficient in the adjoint bundle of the G bundle ρ. And there is a shift by 1. So this is something which is completely wrong if you don't use derived moduli spaces. And now you can see the pairing at the point ρ is just the one induced by Poincaré duality on X, I would say. So if X is a topological manifold, this is just cohomology with locally constant coefficient. And you just use Poincaré duality with respect to the orientation of X. If X is Calabi-Yau, this is now a vector bundle, and you use a Serre duality. And this is just coherent cohomology. So omega ρ is induced by, I would say, Poincaré duality, Poincaré or Serre duality. And the theorem says two things. First, it says that this organizes well in family over the moduli space Z. Two, that it's closed. That's the hard part of the theorem. So, can be defined globally. That's not too hard. And the corresponding pairing here, it's a two form on Z with this funny shift, but still it's a two form. It's a section of wedge 2 of the cotangent shift. So it makes sense to say that it is annihilated by the Durham differential. So I write E is closed, and here I have to be careful. That doesn't mean anything. I mean, there is an extra structure that makes it closed. We'll see something analog for Poisson structures in a minute. So E is closed is really have to be taken with a lot of care. So that's the first step, and this is, say, well understood. So these moduli spaces always carry symplectic form. They have some degree, and the degree depends on the dimension of X. It's 2 minus D.
I'm a bit naive here. The tangent complex of a derived stack is a two-sided complex.
It is.
Okay.
The more it is on the more stacky the thing is, the more it goes on the left, and the more derived the thing is, and the more it goes on the right. So these are one stacks, so there is only one piece on the left, which is H naught. Okay. So point 2, we turn, and this is where I want to explain something. We turn omega. Well, we could try to, we have a symplectic form, and we could try to just quantize it as, how is it called? Fedosov quantization. But we don't know how to do it in this context. So we are using something more powerful. We turn it into a Poisson structure. And I'm going to explain what these are. This is what I want to explain. A Poisson structure. On Z, it has some degree. Now it's of degree minus n because of some, okay. It's the dual of something of degree n, so it's of degree minus n. And so that's the first thing. And the last step.
Is that in the original paper? Or
What?
That's a new.
No, that's the new thing.
That's new? Because that's already amazing for ordinary symplectic forms. So I can only imagine that you
Okay.
use gymnastics to do it.
There were a star at the theorem.
Ah. What does that mean?
So it means that a big part is proven, and there are still some,
Gymnastics. Yeah.
So I put a star. I want to be honest. But still, I think we really made some progress. It's the kind of theorem where you say, okay, if it is a stack and n is bigger than blah, 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 we know. And if it is not a stack, just a scheme, then we know for any n. This kind of thing where you still have some cases where you don't know how to do so. But anyway, this is the new stuff. It's being written down. And this is a technical thing, but I will start from here. I will start from what's a Poisson structure and how you quantize it. And then you use an extended version of considered formality to quantize. So into a Poisson structure, say P, quantize. So I have half an hour to try to explain how this is done. Okay. Oh, yeah, I was talking about quantizing directly as a symplectic object using some kind of methods of quantization. It's not clear that this can be done, really, because there is this case of BG. BG is symplectic in this sense. So I don't know any construction of the quantum group that doesn't use formality in some sense. So, I mean, it's not completely clear that there is anything else than this approach here. The case of BG tells you that you need to use something, a black box of formality type of statement. Okay, this was the introduction. So I want to start by explaining Poisson structures. So here's how we want to do. Let's assume that Z. Assume that Z is an affine, smooth affine algebraic variety to start with. Say spec A. One way to define Poisson structures on Z is the following. It's a complicated way in this case, but this is the way we want to use to define Poisson structures on these Bun G of X, which are rather pathological objects. So you really have to find a way that on an affine looks overcomplicated. So let's take the symmetric algebra over the tangent sheaf. So that's the space of derivations from A to A. It's an A module. I take the symmetric algebra and I put this in degree -1. That's called polyvectors, I guess. And this carries a nice structure. First, it's a commutative graded algebra because it's a sim of something. T1 is of weight 1 for this grading. But it has also a bracket coming from the Lie bracket on vector fields. So it's a Poisson algebra. It's a Poisson DG algebra where the Poisson bracket is of degree -1. Okay. So what's the name? Garchenhaber algebra.
Neenhouse.
Sorry?
Oh, Schouten.
Schouten Neenhouse.
Schouten bracket. Okay.
Schouten Neenhouse.
It's a Poisson algebra. It's a Poisson DG algebra. Let me say a -1 Poisson DG algebra in the sense that the bracket is of degree -1. And the differential here is just 0, just a formal DGA. And so in particular, you can set. I will get lost with the convention. So let's say let L0 of Z will be defined as, I take this guy and I shift it back by 1. So these are polyvectors where TA is in degree 0 now, and this is a DG Lie algebra. DG Lie algebra. And it's a little bit more than a DG Lie, it's a graded DG Lie. Because it's a sim of something. So now Poisson structures can be defined as follows. So say the set of Poisson structures on Z can be defined as a mapping space in graded DG Lie. map graded DGE from what? I take K, put in degree 1, the bracket is 0, and I consider that it's of weight 2, and I send it to this L naught. That's a question. So this is a set, just a set of Poisson structures on Z, and this is the mapping space in the homotopy theory of graded DGE algebras. This is just the standard thing where K is in degree 1 with a 0 bracket. Twist by 2 means of weight 2 because these are graded DGE. And this is the graded DGE, which is this one. And if you look at how this mapping space looks like, it's weakly equivalent to a set, which is just a set of Poisson structures on Z.
Say in the bracket, K minus 1 of 2.
Sorry?
What is this K minus 1 of 2?
So that's the DGE, which is concentrated in degree 1, just K. The bracket is 0,
Okay.
and it's pure of weight 2. This is a graded DGE. Pure of weight 2.
Where is the second grading coming from?
I define a graded DGE. So a graded DGE is a graded complex with a Lie structure, and the bracket must satisfy some, it should be of weight -1 with respect to the graded decomposition.
So there is one grading.
There are two grading. There is a cohomological grading and there is a weight grading. As in here, the cohomological grading, here they coincide, but you will see in a minute that if A is not smooth or if it is a stack, they won't coincide anymore.
So
So there is a cohomological grading and a weight grading.
sure. So you want to allow A to be graded itself?
A will be a DGA at some point. Is it more clear? Okay, there is a notion of a graded Lie algebra. And
So you're not, once A is graded, you won't just be able to take a Murakata element in this guy because it won't be quadratic anymore.
yes,
That's
I
what
want to
you
restrict to
keep
the
in
this
track
wedge
of
2
two
part,
values.
and this is why I want this to be of weight 2. Okay. Unless you find something called generalized Poisson structure, so I don't. Okay, that's what we're going to follow for now. If I have a derived scheme or derived stack, which means essentially that you see algebraic varieties are modeled over commutative rings. Derived schemes are modeled over commutative DGAs, and derived stacks are kind of smooth quotients of this kind of derived schemes. So, for instance, I would have to know what. So when A is a CDGA, this makes perfect sense. But now, if you suppose that you want to apply this to a stack, you get into troubles because this is not a local definition for the smooth topology. So there is no pullback of bivectors along a smooth map. So it's not a local definition. You cannot just say, I do something on local affines and I take, a gluing procedure to do it on a stack. This is not going to work. So you need something global, and that was one of the main technical problems that, symplectic forms are local things. They are just differential forms. So you can glue them for the smooth topology. Poisson structures, you cannot. So we got stuck for a while, actually.
It's état local, but not.
It's état local, but not smooth local.
But excuse me, so even for a symplectic form, if you pull it back along the smooth map, which is not étal, you get something that's degenerate.
Yes, but still the forms glue. The non-degeneracy condition is a global condition somehow, but the form as a closed-to form can be defined locally. So meaning the closed-to form on the stack is just the cohomology of the stack with coefficient in the sheaf of closed-to forms, or a complex of closed-to forms. So they have descent. It's not true for Poisson structures. I mean, we really got stuck for a while. So I will now present a way to do this globally.
Why not just take a Murakata element of the descent L infinity algebra?
No, there is no descent L infinity algebra. It's not even. No, it's not even a sheaf. The thing is,
It's not a sheaf?
this tangent complex here is not even a sheaf of DG Lie algebras over K. Not even. Look at the case of an action of a group on a variety X. This tangent complex is like the Lie algebra goes to the tangent sheaf of X, it only becomes a DG Lie algebra after taking invariance. It's not a DG Lie algebra before. So there is this thing that global sections of the tangent complex is a DG Lie, but it's not the global section of a sheaf of DG Lie. So there is something, I don't know, there is a solution to this, and it turns out that the solution that I will present also prove this extended version of conservative formality. So yeah, we are happy with that, but maybe there is maybe something more simple, but we just don't know. So let me explain how we do this. So now Z is a derived algebraic stack. Typically, it will be of the form. So think that it's something of the form. It's not the same G. So GLN. But there is this locally constant on the board. Okay. We've heard yesterday that on each board it should be constant, but then, so it's not the same G. Okay. So A is a commutative DG algebra now. These are functions on your atlas of the stack. It's non-positively graded, and G acts on A. And you want to, so this is the algebraic description of the structure, but then you have to take the quotient in some complicated category. But algebraically, it's pretty simple. It's just a DGA of representations. So that's the kind of objects I mean by the derived algebraic stack. And I want to define Poisson structures on these things. So there is a tangent complex, which is under some finiteness condition, it's a quasi-coherent complex on Z, even it's a perfect complex on Z. And I want to define the global sections of the symmetric algebra of TZ. Now, for zero-shifted thing, I have -1, so I should have -1 minus n here. And I shift it back by 1 plus n. I call this Ln of Z. We will be fine if we knew that Ln of Z is a graded DGB, and this is not that easy. So the problem is to see is a graded DGB. So essentially the problem is to say what's the Schouten bracket for the tangent complex of the derived stack. Okay, so this is one way to do it. I mean, once we know it's a graded DGB, we can apply the same formula. Okay? So n Poisson structures or Poisson structures of degree n or minus n, I never know. By definition, is going to be this mapping space. To make this definition meaningful, we have to know it's a DGB. And the next step is to relate this DGB. So it's a DGB algebra, so it controls a formal deformation problem. We have to identify this formal deformation problem to the deformation of the category D of Z. And this is where formality enters. Okay, so how the way we found to solve this thing is to talk about branes. So let me say O brane. So that's something quite general, and it can be applied to some specific case where it gives this, but it can be applied to some other interesting case where it gives other interesting things. So what is O here? So O is an operad in derived algebraic stacks. So what are the typical examples of such things? Well, first it can be an operad in schemes, for instance. And there is a general rule how to construct these kind of objects. Assume that I have a topological operad to start with. Then I can turn it into an operad in derived algebraic stacks in the following way. By doing some kind of tensor product. I will explain what it is. I can take the cohomology of this operad, and I get a co-operad in a commutative DG algebras over K. So I should be careful here. Maybe I should put infinity. There are some homotopy coherence issues here, but you can. It's possible to make to give a sense to this. So to have a topological operad, take the cochain complex or a model for it, which is a commutative DG algebra, and then you find a co-operad in commutative DG algebra, and then you take spec of that. It's not really a commutative DG algebra of this type. It's more like non-negatively graded, but the spec makes sense anyway. We can talk about this, and that's how this tensor is defined. This is now an operad in stacks. So any topological operad gives such a thing. I should say, okay, what's the fundamental example I want to use here is the En operad, for instance. So if I apply this to the En operad, O0 is En, the topological En. Then there are various n's now. Let me give a name. So En tensor K, I will write it like big En, just notation. And now if you want to understand what's this big En, I can at least tell you what's En at 2. So it's a stack, and as a stack, it's equivalent to BGA. You have to think about this as the algebraic circle, or the schematic circle. Oh, En, I wanted to say 2. So more generally, En at 2 is it's denoted like this. Usually it's a n-1 dimensional schematic sphere. So it's a stack which looks like this. So pi n-1 is the additive group, but you might, depending on the odd or even case, you might have one more homotopy groups or not. Okay, so if you want, this is a model. Another way to look at it, that's a model for the rational homotopy type of the En operad. It's not really the rational; it's the K homotopy type. So if K is Q, it's really a model for the rational homotopy type of the operad. Okay. There is another source of operad in derived algebraic stacks, is when you start with a Hopf operad, a Hopf DG operad. You can use some spec construction to make it an operad into stacks. And this will be how we consider the Pn operad, the Poisson operad, as an operad in stacks. So other sorts of examples. Now let me start with O0 a hop DG operand. By this, I mean, I'm not sure, I don't know if this is standard, but what I mean is it's an operand in DG co-algebras which are co-unital, co-commutative. Okay. Is it the standard terminology? Yeah. So now I can dualize this thing. Home to K, I get a co-operad in CDGA, the same thing as here. And I can take spec. That's an operad in stacks. So the typical example here will be O0 being, what's notation, Pn, maybe? So that's the Poisson operad, or the N Poisson operad. When n is bigger than 2, Pn is just the homology of Pn. Okay. When n is 1, it's just the Poisson operad in vector spaces. But it also makes sense for n negative, where you have a bracket of positive degree. So in this case, this construction gives me big Pn, which is an operad in derived stacks. And as I can give you some values here to see what it means. Essentially, it means you replace spheres or schematic spheres by formal schematic spheres. So you replace the rational homotopy type by the formal rational homotopy type. So example, if I take P1 of 2, that's a formal zero-dimensional sphere. And a formal zero-dimensional sphere is spec K of epsilon. This is a formal, it's not. Well, you think that way because S naught is 2 points, and if they collapse, they become K of epsilon. And more generally, Pn of 2 is spec K of epsilon. So here it's n minus 1. So epsilon n minus 1 is of degree n minus 1, and it's an infinitesimal. So when n is positive, pointwise, this is the same thing as here. And when n is negative, these are these infinitesimal derived schemes that can be considered as negative spheres of negative dimensions somehow. Okay, and there is an extra. So these are two sources of operad in stacks, and there are also some operad in stacks that lives there without being induced by something, which are operads of modular type. So like the modular operad is an example. It can be the family of things that modular operad. So there are operads in algebraic varieties, say, or in algebraic stacks that already are there. They are not induced by something topological. And it's also very interesting to look at this case for the theorem I'm going to state now.
Is it 0 or is it G?
0, it's 0. I mean, if you want to put G, I'm using just operads, but then you can.
Modular is in moduli spaces.
Moduli space.
The moduli space, yeah.
First modular, you create genus. So
Sorry?
When the word modular, the adjective modular for us is you create genus. Okay.
Ah, so what's the name for this?
It's fine.
Sorry?
They're Deligne-Mumford compactifications of the moduli space of pointed curves.
It's an operad in algebraic stacks. I don't want to look at it as a topological operad.
I didn't say that.
Okay.
Sorry. It's a stack.
No, I just wanted to say that there are also examples of operads in algebraic stacks that are not induced by this kind of. These are the one that comes from homotopy theory somehow. There are also operads coming from geometry. There are, for instance, higher dimensional generalization of these things where you have configurations of PNs and these kind of things. So, I'm going to state a theorem now that also makes sense for this kind of operad with some, slightly technical thing that you have to consider different genius and these kind of things, but and it's a cyclic operad also. Let me just wanted to mention that this also makes sense in this case. Okay, so what's the theorem now? So Z is a derived algebra stack. I will say nice enough. It means with some finiteness condition like quasi-compact, finitely presented, maybe the diagonal should be something. They are all satisfied for the spec A mod G I was talking about. Again, a nice enough operad in derived stacks. Then, and there is one condition. I will leave it like this. It's a condition on an operad. It would be a bit too long to explain. It's just a condition that if you draw some diagram coming from the operad, you ask that these diagrams are homotopy Cartesian. So it looks like a condition which is close to be coherent in the sense of Jacob-Lurie. I'm not completely sure, but at least the same kind of results seems to be true. So there is a condition which I say that O is of configuration type. It's a technical condition. And maybe this has been identified before, I don't know. I didn't have the time to ask experts in operad in this room before this talk, so maybe this is something known, I don't know.
Do you mean kind of that they're a forgetful, you can forget?
Forget is easy because once you have O of 1 and O of 0 being just a point, you can forget.
That you can forget points? I mean...
No, this forgetting point is easy. If you have a unital operad with O of 0 being...
But a wrong way, sort of forgetful, like for your modular.
No, the correct way, I mean the universal curve. Yeah, this makes sense. It's not this, but it's about how this universal object behave under composition. Okay. So it is satisfied for all these three examples. So now I will look at map from O of 2 to Z. That's another derived moduli stack. It's a derived algebraic stack of maps from O of 2 to Z. I'm looking at this clock. Actually, I have 3 more minutes on this one. Okay. I came early this morning to just... So I look at the moduli of maps from O of 2 to Z. O of 2 and Z are 2 derived algebraic stacks. There is a stack of maps. And under this nice enough condition, it's an algebraic stack. And then I put T, the derived category of this thing. Then the claim is that this derived category has an action of O. T is a no monoidal TG category. That's the conclusion of the statement. And this structure here only depends on O, nothing else, in the sense that you don't need extra structures like maps that forget a point or anything. Just have an operad satisfying a condition, you get an action. For instance, if you know that O is equivalent to a prime, then you know that these two things are just the same. Okay, so what's the corollary? The corollaries of this theorem is that everything works, essentially, except the little star at the beginning. So there is one case where it doesn't really work, but maybe it's just that we are not smart enough to understand how it does. But so now, what applications? So first application, we know what are Poisson structures now. How do we do this? We take O to be Pn. Z is our Z, and we have that the derived moduli space of map over 2Z is a Pn category. So in particular, it has a unit. There is a unit element for this action. It is a 1, and I can take endomorphism of 1. And what you can check is that this endomorphism of 1, O of 2 is a formal sphere. This is what I was saying. So endomorphism of 1 is like distributions on the tangent stack, so they give, on the cotangent stack, so they will be polyvectors. So this is exactly R gamma Z sim OZ TZ minus 1 minus n as a complex. And now, this is a Pn category. So this thing has two actions. It's an endomorphism object, so it's C1. And it has an action of Pn because it's the, it's the unit, so it is stable by the operation, if you want. And they are compatible. So it's how was denoted the tensor product? It's an E1 tensor Pn algebra. And there is something like this that I'm sure you're going to believe me. It's more easy than the case En, actually. Yeah, it's more easy. It's more easy. So it's a Pn plus 1 algebra. So I get a Pn plus 1 algebra here, and I'm fine. So if I shift it by n plus 1, I get a Lie structure. I can define Poisson brackets as what I was saying. And we know what are Poisson structures. But we also know formality.
Even on this clock.
Yeah, I'm sorry. 30 seconds. It's not my fault. Ezra asked too many questions.
I haven't finished.
I can't remember how much you take for this. I mean. Okay, so 2. I'm finishing. So formality. I'm finishing with this. So now you can also take O to be this En. And what you find is this R gamma here. Together with the Pn plus 1 structure is equivalent to this higher Hochschild cohomology. It's called En Hochschild cohomology of T. This is a Pn plus 1 algebra. This is an En plus 1 algebra. And by this, I mean I choose an equivalence between these two things by formality. And the claim is that they become quasi-isomorphic. And now it's essentially finished because this is known to control deformations of D of Z as a Lie monoidal TG category. Maybe I should say that this is something you can find in a paper of John Francis. Okay, so this is you have a Poisson structure. It's an element here. You look at it here. You get more Cartan elements, and you get a formal deformation. So this is how it goes. Thank you.
Any questions from people besides Ezra?
Yeah. Thank you. Because this conference belongs to the GBU program, what is the relationship with Grothendieck-Teichmüller group? We know that there is the action of Grothendieck-Teichmüller group on constitutive formality. With respect to the op DG operads structure, does not prove that the operad is exactly GT, exactly by using rational homotopy
Yes.
theory for the
Yes.
operad structure. So have you checked whether this Cotillic Tashmir group is active?
I mean, there is something you probably know better than I. So there are higher versions of this Cotillic Tashmir group. You can take the automorphism of En, filtered automorphism of En, restricted to the identity on Pn, something like this. But it seems to be very close to the Cotillic Tashmir group. So because of this kind of formula, if you have an automorphism of E2, you get an automorphism of E3. So the Grothendieck Tashmiller group acts on everything here. So there is a choice of this kind of formality, and it will act on this choice. But I mean, it's really a part where I don't really understand what's going on. I mean, how these different ends are compatible together is something I don't understand. So you should know better than I.
John?
So the construction you gave of the O-monoidal structure on that category, is it in algebra in O-monoidal categories?
What?
So the thing you erased there, you said that given this condition on the operad, on the lower board.
Yeah, so this T is a no monoidal category.
The O-monoidal category, is it in algebra in O-monoidal categories? So in the case of the En operad, it's an En plus 1.
I don't think so.
Oh.
No, I don't think so. Look at the case n equals 1.
Oh, no, sorry, you're right. What I meant to ask is it the center of the original category of just quasi-coherent sheaves?
I don't know. It could be.
The En case.
Yeah, it could be. I don't know. The thing is, it works for this modular operad there, for which the center is not. I mean, you can define a notion of a center. You see, these operads are really in stacks. So I'm not saying that it's a no monoidal category in the usual sense. I'm saying that, maybe I should write this. What's a non-monoidal category? Something like this. So I have operations, but they are parameterized by the stack O of n. So it's a family. It's an algebraic family of operations parameterized by O of n. So it's not really okay. So maybe I guess you can talk about the center in the category of the hard stack, something like this. It could be that. I don't think that for any O, it is the O center, but for O being Pn, it seems to be the Pn center. At least in the affine case, I think it is. In the global case.
But in the En case, it's the
The En case, I think, yeah, it is. Yeah, but this is, you know better than I also. No, for in the En case, this is what you know. Nothing more.
You said that in Calabi-Yau 3 case, this quantization is related to DT invariance. What do you mean?
On which block? Let me try to be. So you have this G X for D. Now, so the quantization is a deformation of D of Z as a monoidal category. So I was cheating here. You know, when you deform an algebra, you don't really deform the algebra, you deform the category of modules. So here it's the same. When you deform a monoidal category, you don't really deform the monoidal category. You deform the two category of modules. So this is a two category, which deforms D of Z mod. Now D of Z mod, there are sheaves of categories on Z. And the relation with the Donaldson-Thomas theory is that there is a natural object here. So it looks like a sheaf of category on Z, but it's not really. It's like a twisted sheaf. You know, it lives in the quantization. It doesn't live here. And the way you can understand this thing is that this is locally the moduli space is given by the critical locus of a function. And this category is just matrix factorization associated to this potential. And they don't glue in a nice way. So they don't glue as a sheaf of categories here, but they glue as an object here. So locally, this is matrix factorization. And now you have this category called twisted sheaf dt of x. Well, on the nice part of the moduli space is take Hochschild homology of this MF thing. It's a constructible sheaf, take Euler characteristic. That's the number. That's the Donaldson-Thomas.
One more question?
So in this formality, do you see any explicit formulas like Feynman graphs that formula's appearing.
Okay, apparently Damien Calac knows some explicit formula for this. In the affine case, I think.
Right. Well, that's
I have no idea. This part here, for me, is a complete black box. So I know they exist, and that's all. So explicit formulas, I'm not the right person to ask for this explicit formula. But Damien Calac told me that he has a proof of this formality for Z being affine, or he has an idea of a proof, maybe, I'm not sure, that uses Kontsevich's original proof using explicit formulas and graphs and some explicit integrals.
in that case, you can at least say explicitly what the Poisson structure is. It's affine.
I don't know this.
Maybe I can partially answer. I think I will partially talk about this tomorrow. So I think that, I mean, for Pn to En, there's an explicit formula in terms of Feynman graphs by Kontsevic, right? Formality of little n cubes operads. And for the formality morphism, at least, if you look at only the V part or L infinity part, you can just generalize the Kontsevic structure to the Kontsevic formula by integrating over the upper half space, and instead of taking the usual hyperbolic form, you take, you have a volume form on the spheres essentially instead of on the circle. Right? There's a natural way to do that. And for if you want to extend this to really an En morphism, not just the L infinity or E part, that I do not know currently an explicit formula, and I think also Damir doesn't know, because we work together on this.
Yeah, sorry, I've been told this.
But there is, of course, what you can generalize is Tamarkin's proof. So Tamarkin's proof just generalizes up to changing some.
But N here could be negative, or am I wrong?
Yeah, you can, but there is this we can talk after the talk if you want. There is this trick of shifting the form of variables. But maybe I should say that all of these. Okay. Oh,
I suggest that we leave the rest of the questions on this very interesting talk to the break, which we're going to extend to 11:15, so we actually have time to take a proper break. And now we can thank Bertrand for a very interesting talk.